All right, we're going to the second part of the notes. One of the things I want you to do at some point in time, you're going to see this again, you're going to pause on this and you are going to color in basically the same thing you see right here into your page 5. That way you can see, you don't have to do the hot spots purple, you can do them a different color. You can color in the landforms like brown or green or something like that, just so you can see the difference, in a very light blue. But I do want you to indicate the difference, like the blue for the divergent plates, orange for the transform, and red for the subduction plates. You can leave the complex or uncertain plates black, and that's totally fine. And like I said, the mantle spots, I would like you to please do them in a different color besides the 3 colors we see right there. All right. So the world is made up of a bunch of plates all riding on top of the magma layer of the Earth, and this is called the asthenosphere. If you didn't know that, on page 10 of your reference table, it does say it right there. Because of convection currents, if you need to, where it's got, you can see mine at the top right there, you got the red and the blue on the side, you can write down convection currents right there just to give yourself a little reminder. So these convection currents move the plates because you have the hot, light going up and the cool dense going down, magma, liquid rock, and it's causing this circle to go, causing the plates to move. There are 3 types of plate boundaries. So in your notes, this is kind of like flipped from what you have. So looking at what you have right here, you have this little design right here. What I need you to do is you are going to start filling in points. I have all these arrows. You are going to do the same thing on yours, and you are going to place arrows on it so that it matches what I have on this screen. So the first thing we're going to look at is this area right here, right there. Point to right there. It's that the deepest spot right there. That is called a trench, and it is formed only with convergent plate boundaries, where they converge, they come together. You have one plate boundary that is light, and you will see that the density, a bonus from one of our quizzes, the density of granite is 2.7, and that's the continental crust. This is a 2.7, whereas the density for the oceanic or the basaltic is 3. So this is more dense, heavy than this. So when it hits, it's going to push down. The other one's going to ride on top. And they form a trench when they come together. You see that little point that comes in between my fingers? That is a trench. Again, right here, like the Pacific plate right there, your long, this long piece right here, this is going to be the oceanic basalt. What I would suggest is like right here, more dense it sinks. I would also put an arrow pointing that it's going down, pointing the way that it is going. Hint, hint, you may have to see this or do this later. And right at the bottom, right here, you can make it so that it kind of turns into lava or something like that, or magma, because this is where the plate is getting destroyed. You no longer have the plate at this point. It gets destroyed. It gets pushed down so much it melts. It destroys the plate. Right here, this big thing right here, this is granite. It's less dense. I would put continental granite. If I were you, I would also put little volcanoes right there, because typically when you have a convergent plate boundary, you are going to see some trenches. You'll see trenches, you'll see volcanoes, you'll see island arcs. Hint, hint, you may need to write this down. All right, the next thing we have is, we got to skip, this is a different type of convergent plate. So this is oceanic versus continental. And they form what I just said, island arcs, volcanoes. But what happens when you have continental versus continental? Well, they're the same density. So when they push together, there's nowhere to go but up. And when they go up, they form mountains. So on the side, I would put on the side right here, continental equals mountains. You're not going to have lava forming because lava, or not lava, but yes, lava, you're not going to have that formation of the destroyed crust because you don't have one getting pushed down under the other. They're the same density. So they're going to push against each other and push up to form mountains. The next thing we have is a divergent plate boundary. Again, we're going to label some things right here. All right. So the first thing we're going to do is go right towards the middle, right here, and we're going to label that as a ridge. And the thing with the ridge is at the ridge, this is where your crust is being created. You can even write that on here. Crust is being created, and it is the youngest rocks we have on Earth is right at those ridge because all of this is forming crust. And they're both oceanic basalt, and they both push out, right? I would put out like this, out like this. And one thing to know, on the farthest side of your paper, put an arrow and say that's the oldest rock. The farther you get away from the ridge, the older the rocks are going to be. And if you notice down here, I'm going to start drawing in the convection currents. So what is happening is we have the hot magma from the outer core, and it is going to push up. Sorry. Ooh, I skipped ahead. It is going to push up. And when it pushes up, it goes up like this and up like this. It's pushing all of this up. It's out and around, out and around. And then all this older rock, it starts to get cold, starts to get more dense. So then it starts to sink at the convergent plate boundaries. It sinks, and then it heats up at the outer core and then comes back up. It's a cycle. It's a convection current. Next thing we have are right here. These are called transform faults. They go side to side. There's not much to label on this one. However, if you look, I know this one's all written on. You can see everything that I mentioned. I wrote on the side that continental makes mountains. It says convergent. I said volcanoes. And I have all this information written down on mine. And then you have the divergent plate boundaries where they're going apart. They're divergent. And then right down here, you'll notice on the side over here, one of the things it looks like it's so neat and nice and tidy, and they go side to side, and there's not going to be any issues. However, there is. Not all plate boundaries are straight. Now look at this. This is a transform fault. And you'll see it goes straight here. Oh, but then it turns, and then it goes straight there. What happens is it kind of goes like this, where you have one plate boundary like that and one plate boundary like that. They're going the opposite way. And when they push so much, rock can only stretch so much or take so much pressure before it pops. And when it pops, that equals an earthquake. So what I'd like you to do on the side is that right there. Breaks, pops, equals earthquake. Please write that in. Pause if you need to. Right? That's what happens as they go side to side, and they're like this. They're not totally perfect, and they push and push and push, and they pop. And when that pop happens, that's when the earthquake happens. And you'll see this in California along the San Andreas Fault. All right, so the last little bit that we have, you're going to notice the spreading ridge on the back side of your notes. I'm sorry, that page is not wanting to flip. It ripped a little. So it is labeled quite a bit for you. Right there. It is labeled. You've got Part A, Part B, magma, or material from the mantle, spreading ridge. Ooh, this looks kind of familiar, like we've seen this before. This is a divergent plate boundary. At the divergent plate boundaries, you're gonna notice that it spreads, and we have different colors. These different colors just signify that we have different polarities. What it means is we have a normal true north. So our normal true north would be like the I think in this case the dark colored thing, the normal true north. So it'd be the dark one. So normal true north gets pointed like that. It's the darkest one. But every so often, about 200,000 years, our magnetic poles, they flip. So instead of the North Pole being north, it flips so that the South Pole is actually the north. And it's the reverse. It's the reverse, okay? So it reverses so that the north is actually south. And it flips. So every so often it will flip. You do need to write those down. Let's see if there are questions. The dark would be normal, the light is reversed. All right. So we have some questions. What are the plates doing between the Nazca and the South American plates? So if you look on page 5 of your reference table, right here, we're going to look for the Nazca plate and the South America plate. So South America's here, the Nazca's right here. You're going to tell me what's going on right there. What's going on right there is it is converging. What is formed at a convergent plate boundary? Go back to your notes if you need to. You should write, you could put trenches, volcanoes, island arcs. At the mid-Atlantic ridge, what are the plates doing? So the mid-Atlantic ridge is right over here. And what are they doing? Right there. What color is that? That's blue. And my blue means they are diverging. They're going apart. They're going farther and farther apart. Another thing you could write is they're creating crust. What at a convergent what is happening at a plate to the plate at a divergent plate boundary? So they're moving away, they're creating crust. Number 5, at a convergent boundary, what is happening to the plate? Converging, coming together. They're coming together, and what happens with that? It destroys the crust. So a divergent creates it, a convergent destroys it. At a divergent, number 6, plate boundary, where is the plate the youngest? So when we're looking at this, where is it the youngest? You're going to say closest to the ridge. Where is it the oldest? Farthest from the ridge. Number 7, name 2 plates that are transforming. There are a whole bunch. You can choose whatever 2. Ones that I like are North America and Pacific plate. That's at the San Andreas Fault right there. You can do the Scotia plate and South America plate, the Antarctic plate and the Scotia plate, the, let's see, Antarctic and the African plate. There's a bunch. Wherever it is orange, you're going to write that. You can write any 2. What forms at a transforming plate? The only thing that occurs at a transforming plate where they go side to side is earthquakes. That's what you get there. Not that you don't get earthquakes at any of the other ones. These ones typically not so much of the earthquakes, but convergence, yes, because as you push and push and push, you're putting a lot of pressure and eventually it pops. When you get that pop, that's when you get tsunamis forming on top of earthquakes. And if you didn't notice, over the weekend in Japan, they had a 7-point-something earthquake, and right after that, they had a tsunami warning. So, number 9, finding the boundary between the Indian, Australian, and Eurasian plate. What are they doing? So here's the Eurasian right here and the Indian Australian. And when you look right there, what are they doing? They are converging. They're coming closer together. Look closely. It's two continental plates that are the same density. When two plates of the same density hit each other, they have nowhere to go but up. And that forms mountains. Mountains are formed, and in that location, the highest mountain in the world, Mount Everest. All right, we are done with notes. If you have any questions, please don't hesitate to ask. And I hope you guys have a great day.